Welcome to FORSEdu.
In continuation with our series of Total Quality Management, we present to you the fourth episode of the series. Our topic for today's video is SPC using control charts and process capability index.
Meet Mr. Johnson, the quality control manager of ABC soft drink company. He is very tensed nowadays because the percentage of
defective products, that is, underfilled bottles being manufactured by his company, is around 15%, which is quite alarming. He needs to look into the matter urgently, and employ more efficient methods of quality control to cut down on the percentage of defects. For doing this, he decides to use different methods under statistical process control, like control charts and process capability index. Statistical process control is a method of quality control which employs statistical methods to monitor and control a process. This helps to ensure that the process operates efficiently, producing more specification-conforming products with less waste. The most commonly used and effective SPC tool is the control chart. It uses statistical formulae to determine whether a business process is within the control limits or not. A control chart has three different lines, namely, central line or average, lower control limit, LCL, and a upper control limit, UCL. In the diagram, the upper yellow line indicates the upper control limit, the green line indicates the central line and the bottom yellow line indicates the lower control limit. The distribution of the different sample observations is indicated by the red line in the graph, showing that process is in control. There can be four major types of variations in the pattern of control charts. The following two figures show that the process is off-centered. The first one shows sample observations, mostly concentrated towards LCL, and the second one, near UCL. The next two figures indicate that the process is presently within control, but the current trend will make it exceed the control limits. From the diagram, it can be observed that control charts are of two different groups, based on the type of data, variables, and attributes. Each of these groups can be further classified into subgroups, variable data being of three different varieties. Similarly, attribute data can again be subdivided into two categories, defectives and defects. A control chart for variables is used to monitor characteristics that can be measured and have a continuum of values, such as height, weight, or volume. Some examples can be the weight of a bag of sugar and the temperature of a baking oven. A control chart for attributes, on the other hand, is used to monitor characteristics that have an attribute requires only a single decision, such as yes or no, good or bad, acceptable or unacceptable, examples being the apple is good or rotten, the meat is good or stale, the shoes have a defect or do not have a defect. Major types of control chart are X bar and R chart, P chart and C chart. First, we see what is a mean or X bar chart. This chart is used to control the variations in the average quality standard of the products. To construct this chart, we first compute the individual sample means. Then, we take the average of all the sample means to finally construct the central line. To construct the lower and upper limits of the chart, we use the following formulae. Next, we have the R chart. It is constructed to monitor the variability or dispersion of the process, using sample ranges. The formulae for the center line, LCL and UCL, are as follows. The terms have usual meanings. Next we have the P chart. It is used to measure the proportion of items in a sample that are defective. Examples are the proportion of broken cookies in a batch, and the proportion of cars produced with a misaligned fender. To construct the upper and lower control limits for a P chart, we use the following formulae. C charts count the actual number of defects. For example, we can count the number of complaints from customers in a month, the number of bacteria on a petri dish, or the number of barnacles on the bottom of a boat. However, we cannot compute the proportion of these defects using chart. The formulae for calculating UCL and LCL for C chart are as follows. Let's take a numerical example. to explain how these concepts are applied in reality. The table below shows the number of defectives found in the inspection of 10 lots of 100 items each, in Mr. Johnson's cold drink company. To answer the following two questions, we first need to calculate the various control limits using a P-chart. We first find P-bar. Then, we calculate the values of UCL and LCL for P-chart. Since P-bar cannot be negative, LCLP will be 0. From the above plot of P-chart, we can observe that the sample 7 is out of control. Hence, the process is still not in control. Now, we first eliminate the 7th sample, and calculate the P-bar, LCL, and UCL values, again. Considering the new values, it is found that all the remaining values are within control limits. Hence, we can finally say that the process is now in control. Mr. Johnson also wanted to find out whether the production process was operating within the given specifications or not. And one of the best method to do that is using process capability. Let us first understand what is process capability. A critical aspect of statistical quality control is evaluating the ability of a production process to meet or exceed preset specifications. This is called process capability. To understand exactly what this means, let's look more closely at the term specification. Product specifications, often called tolerances, are preset ranges of acceptable quality characteristics, such as product dimensions. For a product to be considered acceptable, its characteristics must fall within this preset range. Otherwise, the product is not acceptable. The chart here shows that the process is under control as it is within the lower and the upper specification. Whereas this chart shows that the process is not under control as the process distribution exceeds the upper and lower specifications. Process capability is measured by the Process Potential Index, CP, which is computed as the ratio of the specification width to the width of the process variability, where the specification width is the difference between the upper specification limit, USL, and the lower specification limit, LSL. The CP index does not take into consideration the placement of process with respect to the given limits or the specification width. In simple terms, if the process is off-centered, then it is not considered for calculating CP. The drawbacks of CP are remedied by CPK, which is called Process Capability Index. Both are very similar, but the latter considers the centering of a particular process distribution. This shows the formula for calculating CPK. It can be said that it measures the variations between the target and one specification, either CPK low or CPK high. Let us look at an example. 3 bottling machines at ABC Soft Drink Company are being evaluated for their capability. Bottling machines A, B and C have standard deviations 0.05, 0.1 and 0.2 respectively. If specifications are set between 15.8 and 16.2 ounces, determine which of the machines are capable of producing within specifications. To determine the capability of each machine, we need to divide the specification width by 6 standard deviation for each machine. The given table shows the calculations. Looking at the CP values, only machine A is capable of filling bottles within specifications, because it is the only machine that has a CP value at or above 1. Now, looking at the figure, we can see that the process mean is 15.9 and the process standard deviation is 0.067. Upon calculation, the CP value of 1.00 leads us to conclude that the process is capable. However, from the graph you can see that the process is not centered on the specification range. Here, using only the CP measure would lead to an incorrect conclusion in this case. Therefore we need to calculate CPK. Computing CPK gives us a different answer and leads us to a different conclusion. Here, the computed CPK value is less than 1, revealing that the process is not capable. That's it for today's video. Like, share and comment. Stay tuned for our next video.